You know how it goes. Imagine a typical week in ops. Everything seems perfectly fine on the surface, but underneath, there's a silent killer at work. The instability you're noticing, those weird random latency spikes, the unpredictable autoscaling, that is usually the real production incident. It's not the final dramatic out-of-memory crash that makes the pager go off. It's actually that slow, agonizing period of degradation right beforehand that causes the real pain. So, welcome to today's explainer. We are going to validate that pain you've been feeling and decode exactly what is happening inside your systems.
I am super excited to dig into this with you. Today, we're doing a full forensic investigation into the true anatomy of a Node.js memory leak. We're going to look way past those surface-level symptoms and get right down into the nitty-gritty engine mechanics. As you'll see, our natural intuition about how memory leaks work is often completely backwards.
All right, let's map out exactly what we're covering today. First, the deceptive symptoms. Second, the pathology. Third, the misdiagnosis. And finally, number 4, the cure. Okay, kicking things off with part 1, the deceptive symptoms and how memory leaks actually look out there in the wild in production. If we track the creeping evolution of a leak over time, it looks a little something like this. See, most real memory leak incidents don't just start with a massive crash. They begin with these tiny, annoying inconsistencies that nobody really trusts enough to escalate. On day 1, maybe your Node API service consumes just a tiny bit more memory. But hey, CPU and error rates look fine, right? But by day 2, the secondary effects start showing up. Your P99 latency gets all wobbly during traffic spikes. Day 3 brings in this totally unpredictable auto-scaling behavior, mostly because your new pods are immediately inheriting all the elevated load from the degraded instances. And by day 4, your garbage collection is working overtime, but your dashboards are only showing you aggregate averages, completely hiding the spikes. Meanwhile, infrastructure like Kubernetes is acting like a silent assassin. It's just quietly restarting your containers so fast that nobody even notices until it's way too late. What usually happens here is engineers initially point fingers at downstream services, like PostgreSQL or Redis, because, well, the application technically still works. But here's the absolute crucial takeaway. The real incident is almost never an explosive out-of-memory crash. The reality is a gradual loss of reclamation efficiency. The most dangerous leaks are retention leaks. Long before the process actually crashes, the service just becomes operationally unstable. Moving right along to section 2, the pathology. We're going deep inside Node's V8 engine. To really understand this production leak behavior, we have to understand how V8 treats the lifespan of an object. Most short-lived objects start off in what's called new space. In new space, minor garbage collection is incredibly cheap. It's practically designed for rapid allocation and quick disposal. But here's where it gets dicey. Objects that survive repeated garbage collection cycles get promoted into old space. And that promotion right there, that's exactly where your production incidents begin accelerating. Once objects are dumped into old space, garbage collection gets significantly more expensive. It requires a deep traversal of the heap and these brutal stop-the-world pauses that literally halt your JavaScript execution entirely. Nothing moves. Under sustained production load, these pauses amplify your latency and create this deadly, vicious cycle. Think of it like a domino effect. Step 1, a major garbage collection pauses execution. Step 2, because of that pause, the event loop completely stalls out. Step 3, concurrent requests start piling up and your queues expand. And step 4, because there are now way more in-flight objects existing all at the same time, memory allocations spike again, which, you guessed it, triggers even more garbage collection. Eventually, your app is spending a massive chunk of its time just taking out the trash instead of doing actual useful work. This is exactly why memory leaks show up as latency incidents way before they show up as crash incidents. Now for the plot twist. And this is a wild one. V8, it's actually functioning perfectly. That's right, garbage collection is strictly designed to only remove objects that are completely unreachable. The real problem is that your app is essentially acting like a hoarder. It's holding on to perfectly valid, reachable memory that it just absolutely refuses to let go of. So what's actually causing this? Well, let's look at some common culprits. And honestly, we've probably all been guilty of these at some point. We're talking about long-lived singleton objects, infinite cache growth, event listeners that just hang around way beyond their intended lifecycle, background jobs that retain massive closures over huge datasets, or streams that just fail to release references when something goes partially wrong. The really scary part about all of this, these retention leaks sail right through code review without a second glance. Why? Because they look like completely valid business logic. In isolation, nothing looks obviously broken. All right, part 3, the misdiagnosis and the engineering trade-offs we make.
You eventually realize that most memory leaks aren't caused by someone writing a terrible loop or a dramatic typo, syntactic errors. No, they're caused by lifecycle failures, which are architectural trade-offs. For example, you might turn on aggressive caching to speed up throughput, but oops, you just accidentally built a permanent unbounded database right inside your RAM. Or maybe you use large batching operations to save on network overhead, but that creates massive temporary allocation spikes that force objects straight into old space. Systems that are aggressively tuned just for raw throughput often turn out to be surprisingly fragile under heavy concurrency, mainly because garbage collection behavior was never treated as a first-class design constraint.
So, when faced with this creeping, annoying instability, what's the knee-jerk reaction? When the pager goes off, ops teams usually ask the most common, seemingly logical question. Hey, should we just throw more RAM at the container? And the definitive answer to that is a massive, resounding no. Absolutely not. Adding memory is literally just feeding the beast. Increasing the memory limit might mask the problem for a little bit, sure. The app technically has available memory now, but reclaiming that memory becomes so much more computationally expensive. The leak survives longer, it hoards more retained objects, and eventually it triggers even heavier garbage collection cycles. Those stop-the-world pauses we talked about, they become incredibly destructive. You haven't fixed the incident, you've just made it evolve slower and hit harder.
Adding to the whole headache is how we actually monitor these systems. This is where our dashboards can straight up lie to us. Look at the critical difference between heap memory and RSS, or resident set size. Heap memory is just your V8 managed JavaScript stuff, but RSS, that's the whole shebang. It includes the heap, plus native modules, buffers, fragmentation overhead, and everything else happening outside the managed heap. So your service can look totally flat and happy at the heap level, while your RSS is just secretly ballooning in the background. Teams can completely miss the container level pressure entirely until Kubernetes steps in and starts killing pods.
Which brings us to our final section, part 4, the cure. Let's talk about memory-safe system design.
Memory-safe architecture is really all about containment. If you want to prevent those cascading latency effects, you've got to put up strict guardrails. You need to isolate your high-retention workloads into separate workers. You absolutely have to define clear expectations for an object's lifecycle. Know exactly what is just request scoped versus what is process scoped. You've got to avoid holding on to entire massive datasets all at once during transformations. And wherever you possibly can, you need to swap out data accumulation for streaming. This really requires a shift in how we think. Experienced engineers stop treating memory like it's just some background implementation detail. The real mental shift here is thinking in terms of object lifetime rather than object creation. Most production systems allocate enormous amounts of memory every single second without breaking a sweat. Rapidly creating memory is rarely the actual problem. Because here is the absolute golden rule of Node.js performance. Allocation is cheap, retention is expensive. Period. That is the core architectural truth. Having strong observability completely changes how you respond to these incidents. Senior teams aren't just staring at absolute numbers. They're monitoring heap growth trends over time. They're correlating the duration of garbage collection directly with latency spikes. They're looking at the big picture of exactly how long these objects are staying alive. So as we wrap up this explainer, I want to leave you with a provocative question. Something to really challenge how you're monitoring things right now. Ask yourself, are you merely detecting crashes, or are you actually identifying when your runtime begins losing reclamation efficiency? Because I promise you, by the time those out-of-memory errors finally pop up on your dashboard, your application has probably been silently suffering for hours. It's time we rethink how we design and monitor our systems. Thank you so much for hanging out with me for this explainer, and I really hope this transforms how you look at memory under production stress.